Hi everyone, thank you for that introduction. This is my first viticulture conference and I'm really excited to be here. So I changed my title a little bit from what's in the program because I really want to focus today on light sensors and their applications for grape disease management now and in the future. And of course throughout this talk there are going to be some inferences into general viticulture. But I thought I would just start with a quick introduction to myself since this is my first time with this community and many of you meeting me. I earned my bachelor's at Rutgers University and born and raised in New Jersey. And then I earned my master's in applied statistics/data science. We call it biometry, but most people don't know what that is, as well as my PhD in plant pathology at the University of Wisconsin-Madison, working with Amanda Gevin's applied potato and vegetable pathology program, as well as Phil Townsend's environmental spectroscopy. Broadly, my work focuses on applications of hyperspectral remote sensing for disease management in specialty crops, with a more specific focus on pre-symptomatic late blight detection in potato. Starting next week, I will officially be a Cornell faculty fellow at the Jet Propulsion Lab, the collaboration between NASA and Caltech, where I'll be working with the Grape remote sensing project, expanding this project to include aerial and satellite hyperspectral and thermal remote sensing for grape disease detection. And I was really grateful that Cornell allowed me that opportunity before I start as a new grape pathologist in February. So broadly, my research focuses on two main themes, detection and disease differentiation. So with detection, how can we achieve remote pre-symptomatic quantification of the disease impact on plant physiology and morphology, as well as biochemistry in order to make those early management interventions? And also the real gold standard for this remote sensing when it comes to disease management, which is disease differentiation. We need to be able to say when you have one disease versus another, because how you control powdery mildew is vastly different from how you control downy mildew. So using pathogen biology and comparative disease physiology as a framework to understand and apply spectral data towards this goal of in-field disease identification. So with that out of the way, here are the three main questions that I hope you walk away with answers from after the end of this talk. The first of which is actually three mini questions, which are, what are light sensors, what can they do, and also what can't they do, which I really think is the most important of those three. Next, how can commercially available sensors be used for grape disease management currently? And finally, what's on the horizon and what can we expect to have in a couple years' time? So throughout the course of this talk, we're going to be filling out this cheat sheet, which will be available in the conference proceedings. We're going to start with a little bit about the 5 most common types of light sensors and what they are actually measuring, as well as their applications and considerations, because there is no such thing as a magic sensor. As James highlighted, which I really appreciated, is that we really need to be decision pull rather than technology push. There's no such thing as a magic sensor, and they all have their different considerations. And then moving into use cases and a bit on IPM. So I want to zoom back out and start with the real broad picture, which is what is a sensor? And this is just a definition I took right out of the dictionary, which is that a sensor is a device that is responding to a physical stimulus such as heat, light, sound, pressure, or motion, and transmits a resulting impulse for measurement or action. So I've bolded light here because I'm only going to be talking about light sensors today, and we're going to hear a lot about different other types of sensors later on. We interact with light sensors on a daily basis. Our smartphone has just about 1 billion different light sensors integrated into it. And light sensors actually work pretty similarly to our eyes at the most basic level. When we look at this green box on the screen, the reason why it appears green to us is because green light is hitting this box and reflecting, and our eyes are seeing it. Sensors also see that reflected light, but they quantify it. The reason why sensors, and light sensors in particular, have such great applications in agriculture is because of the way that light actually interacts with plants. Light will enter the atmosphere, and then when it hits vegetation, it will do one of 3 things. It'll either be transmitted through the plant, some of it will be absorbed for photosynthesis, but the majority of it is actually reflected back. And that reflected light can be quantified by a sensor as distantly placed as something in space on a satellite. So light is reflecting off of plants, but what really yields these interesting applications is the fact that our healthy and unhealthy plants will reflect light differently. A healthy leaf will absorb blue and red light for photosynthesis and reflect back green and near infrared light. whereas an unhealthy leaf will reflect back red light because it's not conducting photosynthesis properly, and therefore it will reflect less green light, as well as less near-infrared light. So how the light is actually reflecting off of vegetation tells us information about plant health. And light can tell us a number of different things about plant health, such as drought stress, nutrient stress, and disease. And our eyes can also tell us these things about plant health, but all these different types of stressors will cause light to reflect differently long before we can see those impacts with our eyes. And that's because they're changing lights in the spectrum that we can't actually see, which is why sensors are so cool, because many of them are capable of seeing more light than our eyes can see, as well as more specifically quantifying light that we can see than our eyes are capable of. If we first orient ourselves to this spectrum, on the left we've got our gamma rays and also our UV. In the center we have visible light, which is actually a really small portion of the overall light that exists, and then we move into the infrared, and on the far right we have radar, radio waves, and broadband waves. So now I'm going to talk briefly about the 5 main types of sensors. We first have our digital cameras, which operate within the visible light range that our eyes are also operating within. We then have LiDAR, which is actually a laser, and it operates at very specific bands in the infrared range. We have thermal sensors, which operate ways out into the infrared and are actually measuring plant temperature. And then we have our 2 main types of visible plus infrared sensors. We first have our multispectral sensors, which are measuring light in discrete chunks. So this is the type of sensor that an NDVI sensor is. We also have our hyperspectral sensors, which measure light continuously. So both the multispectral and hyperspectral sensors can measure at different ranges of light. They could be solely in the visible range, or they can both extend ways out into the infrared. You'll hear these referred to as V-near or V-SWIR sensors, and that's indicating how much light they're measuring. But the key difference between them is how they are measuring the light. Multispectral is discrete chunks, whereas hyperspectral is continuous and therefore has more variables to assess plant health with. So, I want to say before we go on that once again, there is no such thing as a magic sensor. They each have different considerations when it comes to economics, scalability, and also commercial readiness. So if we dig into each one of these briefly, I want to start with our digital cameras, which I like to think of as eye extenders, because they're phenomenal for seeing things that our eyes can also see, but at different scales than we could feasibly sense with our own eyes, such as at a much broader scale, a much finer scale, much more rapidly, or much more slowly. They have a wide range in terms of costs. They can be hundreds of dollars or even just like $10, all the way up through the thousands of dollars. And their considerations are that because they're only working in the visible range, that they yield limited information, but they have some major pluses in that they are very readily available, they're easy to use, and they're small yet powerful, which is important when you're considering different deployment options, such as on a drone. Next, our multispectral sensors, which you'll remember measure light discretely, are really phenomenal for general crop stress detection because they are capable of indirect problem identification. They're very flexible. Because they're measuring light discretely, they also are budget flexible. They're much cheaper to produce. But their considerations are that they once again are yielding limited information, and they are imprecise due to the fact that they're not measuring the full spectrum of light and they're not measuring it continuously. And this is the advance that our hyperspectral sensors represent, is that they are measuring light continuously and therefore are capable of direct problem identification. And when they're measuring the full spectrum, so something like a V-SWIR, when they're going pretty far into the infrared, they're capable of specific trait quantification, things such as changes in biochemistry and physiology. They're actually capable of quantifying that rather than making indirect inferences from general crop health. They have major considerations, though, in that they are insanely expensive, and they're really not accessible for anyone these days who wants to, own a in-the-black operation. And they are in desperate need of commercial development, and they're kind of in that TRL valley that James was talking about. They're right in the middle. There are no more Nature papers really about hyperspectral sensors, which is a bit of a bummer for an early career researcher like myself. But they are definitely not in that commercial development phase. They're really right in the middle. So, and that's why they also still require expert interpretation. They are just not at the stage where you can have the average trained person look at this and understand the input. You still need someone with a master's or a PhD to manipulate the data and make inferences from it. Moving on to our thermal sensors, these are sensors that are measuring plant temperature and therefore properties that are changing plant temperature, such as water, which is one of the major drivers of plant temp. These are kind of in the middle in terms of the cost range, and they're also at the point where they're almost at that self-service level. They're farther towards the commercial side than our hyperspectral sensors are certainly, but not so far advanced as our digital cameras and multispectral sensors. The high resolution ones, the super powerful ones, they tend to be heavy, which is a major consideration when you're trying to mount something on a UAV. And also the data will very easily become noisy and difficult to interpret with changing environmental conditions. And finally, we have our LiDAR sensors, which are once again our laser sensors. And because they're a laser, they're capable of measuring properties that relate to the physicality of your vine. So things such as plant structure, height, mass, also ground elevation. These are at the farther side in terms of cost, and for a lack of better word, they're just kind of finicky. They're just difficult to work with, even though they are very powerful. They're also incredibly heavy, but you can't mount them on the ground. Because they're measuring the physical distance that your laser is traveling, they have to be mounted in the sky. So it's a major consideration if you want to use something like this on a drone. It's most often placed on an aircraft. So before we move into the second part of the talk, I want to hone in for a second on the most commonly known type of multispectral sensor, which is an NDVI sensor, which stands for Normalized Difference Vegetation Index. And honestly, I truly believe that NDVI is one of the best tools that we have for general crop stress detection, and it allows you to send scouts out to specific areas. But once again, it is an indirect problem identification mechanism. You can't use it to say what is actually wrong with your crops, but it's a very sensitive metric to unhappy plant syndrome. So it'll be able to tell you if there is something wrong, but not necessarily what it is. And NDVI works by measuring the difference between your near-infrared and red reflected light over the sum of that. And that's why it's such a sensitive metric to things that affect plant health, because those are the two types of light that are most strongly affected by negative plant health and most broadly negatively affected. So I just want to really hammer this in, is that NDVI is not capable of specific crop stress detection. And once again, this is a metric that we've had since the 70s, and it's powerful in that you could stick it on a satellite and use it to quantify biomass across the entire globe. But it cannot tell you if you have viral pressure or if you have water stress. So all this annotation on this graph over here, that was done by scouts. So moving forward to how can these light sensors actually be used for integrated disease management? And if you only take away one thing from this talk, I hope that it is much like fungicides, knowing how sensors work or don't work is really crucial to using them effectively. So let's dig into some of these general use cases. Once again, digital cameras are really fantastic eye extenders, and they're really great for properties that we can see over a wider range. Things such as greenness, growth, weeds, pests, visible disease. If you can see it with your eyes, or if you could see it with your eyes, if you had bigger eyes, much wider range, or if you could see things much more slowly, digital cameras tend to be really great for that. Our multispectral sensors, once again, are really great for general crop stress detection to multiple responses, such as nutrient deficiency, water stress, weeds, pests, diseases, but once again, it's not capable of differentiating between those. Our hyperspectral sensors, though, those are the sorts of sensors that are capable of that specific biotic and abiotic stress differentiation, and this is because they can detect and quantify precise physiological and biochemical changes in those later, farther to the right wavelengths of light. And this is the sort of sensor that is capable of pre-symptomatic disease detection. Our thermal sensors are great for those properties that are changing plant temperature, which is most strongly driven by water content. So things such as water stress or pests and diseases that are changing and affecting the plant vasculature. And finally, the LiDAR sensors are really fantastic for elevation and those physical properties associated with vines, such as plant height, leaf volume, as well as canopy density. And you can make indirect inferences with this data towards what sort of management decision you want to do. But once again, this would not be a direct inference. So I want to dig into digital cameras and multispectral, since those are on the farthest right of that TRL scale. Digital cameras and multispectral sensors can be used for crop growth stage determination, for precision timing of important sprays, as well as the detection of residual leaf debris for sanitation. You could potentially use them as well to determine if you have adequate spray coverage, as well as we're developing smartphone apps to assist in diagnostics. And once again, the most commonly known, NDVI is very useful for targeted scouting and general crop health assessment. So if you've heard of, so many of these sensors are offered as like a product service package. If you've heard of VineView, Taranis, Series Imaging, these are just a handful of companies that offer that service arm. And all those normal service considerations apply when you're considering any one of these. Are you happy with the customer service? Do you feel as though the data is interpretable? And most importantly, is it cost effective for your operation? So just because the sensor seems really shiny and great, if those things don't work, then it's not worth pursuing. And finally, I do want to highlight again that there's currently no commercial in-field hyperspectral system available, but that's just for now. In a few years, that will definitely change, and we're really hoping to push hyperspectral sensors out of that kind of valley of death in the middle towards the commercial development. They're also really great for year-over-year hotspot detection and disease pressure monitoring. So this is an example of NDVI being used for phylloxera infestation, which is a pest and not a disease. And it's showing the relative change in pressure and incidence year over year. But the reason why this was such a successful application was, one, because the vineyard didn't really have any other problems going on, and two, they already knew they had a phylloxera infestation that they really wanted to manage. Which leads me to this quote that I really appreciate because it kind of highlights the state of the union when it comes to remote sensing in viticulture, which is that remote sensing can identify and map areas of poor or variable vine growth and track their development over time, but it does not explain the causes of poor vine performance. For this, the vineyard manager must interpret the information provided by the imagery and follow up with on-the-ground investigations. And that's kind of where we are. We need to have scouts out to determine if what we're seeing is accurate. We're not at that automatic trust stage yet. But I think that is where we're going in the future. In the future, we can foresee there being in-field hyperspectral systems performing automatic disease detection, doing things such as pre-symptomatic detection, detecting infection during latent periods of pathogen growth, as well as potentially determining whether or not your isolate is fungicide resistant. You can also use this to help understand precise disease impact on different varieties, and most importantly, combining all these things to inform early management decisions. You can also see the aerial and satellite applications of these sensors being particularly useful on a regional scale, and you could potentially have a hyperspectral informed regional warning systems for disease stress based on the capacity of hyperspectral sensors to measure and quantify those physiological and biochemical changes. So our current disease forecasting models assume that the pathogen is always present, whereas we could potentially use hyperspectral satellites to help us actually know when disease is present. We can also potentially detect the chemical cascade that goes out when a plant is under infection in order to lead to a general risk evaluation or a general regional stress detection. So just some important takeaways. Once again, there's no such thing as a magic sensor. You really need to decide what information is important to you first and then look for a sensor that can get you that. Much like fungicides, knowing how these sensors work or don't work is really crucial to using them effectively. Commercially available sensors do have current usefulness in vineyard IPM, but there's still a lot of research, validation, and commercial development needed before we really see, especially our hyperspectral sensors, thermal, and LiDAR, really truly integrated into everyday vineyard management. Specific stress detection and differentiation is not yet commercially available, And our hyperspectral sensors in particular really need that commercial development. So this is our filled out cheat sheet. This will be in the conference proceedings. I was gonna bring it with me and I forgot, so I apologize. And if I have any time, I will take some questions. Thank you all for listening. One question?
We have time for one question at least.
Oh.
Oh, sorry. Sorry.
No, just, I'm curious, your perspective on grapes. I know you're just starting
Yeah.
to think about this, but what diseases would be the most, reasonable targets for a young faculty member starting off? What will you be working on?
So my experience thus far has been pretty strongly in omycetes. So I am hoping to focus on downy mildew as I've learned that it's a very important pathogen here. And also I'm looking to work on botrytis, powdery mildew, sour rot, whatever seems most needed by the industry. I'm also particularly interested in trunk diseases just because I really kind of like the challenge of trying to detect something that you can't see with your eye that doesn't have super visible signs of disease stress, even at the most intense phases. So those are some of the things I'm hoping to focus on. But I am looking for industry response here. So
Thanks, Jay.
I can take questions later. Thank you all.